All right, how does an MRI work? And how does it produce an image? I'm going to try to do this as simple as I possibly can without using too much technical work. All right, so we're going to be looking at the human body, and we're going to be looking inside the human body without cutting the person open. So how do we do that? First, we look at atoms inside of the body, and we're specifically looking at hydrogen. Now, why do we use hydrogen? Well, the body is 70% water, and water is made up of H2O. Now, we don't put the one there if there's only one, but there's 2 atoms of hydrogen, 1 atom of oxygen. So, if there's 2 atoms of hydrogen in every atom of water, molecule of water, how many atoms of hydrogen are in the human body? That's 1 octillion, or 1 to the 27th, or 10 to the 27th, and that's 27 zeros. So 27 zeros. So there's quite a few. So now we know that there's an octillion, or 10 to the 27 hydrogen atoms. We can begin to tell you how we're going to use these hydrogen atoms in an MRI. Now there are three types of magnets, rather. The first is a permanent magnet. That is a refrigerator magnet. This is a permanent magnet. It's always on. The second type is an electromagnet. Now, an electromagnet is different than a permanent magnet because it needs power to create a magnet. So there's a bunch of windings around a coil. You apply electricity, and whammo, you have a magnet. The third type, which is what we'll be talking about today, is a superconducting magnet. Now, superconducting magnet is very different than the other two, is that once the electricity is put into the magnet, it always stays in the magnet. And we're going to go over that really. There are permanent magnet MRIs. There are electromagnetic MRIs. Those are kind of going the way of the dodo bird. Nobody really uses them anymore. They're kind of expensive to fix once they break, and they don't really have great image quality compared to the magnets of today. So, we're going to be talking about a superconducting magnet. Now, a superconducting magnet is, imagine if you will, a big coil, and then windings of a specific wire around that coil. The field strength, or Tesla, of any given magnet is determined by how many coils or wraps of that wire around the coil there are, and how much current you put into the magnet. So, let's say you're working on a Siemens Esprit magnet. That'll have X amount of windings, and we inject via a power supply roughly 500 amps of current. And we do that using around 10 volts to push it into there. So once we have our 500 amps of current using the 10 volts to push it in there, we get roughly 1.5 Tesla. To give you an example of how strong that is, the Earth's magnetic field is 0.9 So 65 nanotesla. So this is 9 zeros to the right of the decimal point, and this is 9 decimal points to the left of the decimal point as relations to the field strength of the Earth. So, superconducting magnet is always on. We keep it cold using LHE, or liquid helium. And that is at 4 degrees Kelvin, is roughly negative 452 degrees Fahrenheit. The reason why we use liquid helium is that it is a liquid at 4 degrees Kelvin and it is a gas at 4.1 degrees Kelvin. The reason why we use it again is it's so cold that once all that current is in the superconducting magnet, it cannot change to heat, and therefore the current stays in the magnet for as long as the helium in the vessel is a liquid. As soon as it is not a liquid, we have what's called a quench. It turns the heat from all that current, and it boils off the liquid helium because it boils off very fast. I'm not going to get too much into that. I can talk about liquid helium for another 4.5 hours, but we're not going to do that today. All right. So now that we know we're using a superconducting magnet, we know we're going to be imaging hydrogen in the body. What actually happens? So imagine, if you will, that this is a side view of the inside of the MRI. And then the patient would be roughly inside of the magnetic field, which is at 1.5 Tesla again. All right, so inside of the MRI, there's called an imaging volume. And that imaging volume is right in the center, or isocenter, of the magnet. So all the lines of flux from the magnetic field are pulling in this way and from every direction, if you can imagine that. And they create a 50 centimeter sphere in the middle. So whatever is inside this sphere, whether it be your head, your elbow, your chest, your abdomen, your knee, is going to be inside that imaging volume. So how do we get an image of that? Well, this is where we're going to use the resonance portion of the MRI. So magnetic resonance imaging, we're going to be using the resonance portion of this to get an image. Now, like I said, I'm not going to get too crazy, but I'm just going to kind of give you the basics of it. So we're going to start with the imaging volume. So let's say we're doing a head, and this is the imaging volume we just talked about, and the person's head is inside of there. This isn't to scale or anything, but these are your hydrogen atoms. It's kind of visual representation of what they look like. So as the hydrogen atoms are outside of the magnetic field, they're doing this right here in my hand right now. They're spinning like this, and then they're also spinning in every other direction. The reason being is the Earth's magnetic field pulls on everything. So these are spinning this way, and they're kind of going around and bumping into everything else. Not only that, but as they spin or process, they create an additional magnetic field. So all these atoms are spinning around, bouncing into each other, bumping into each other. They're all still processing. They're just kind of in a random jumble. Imagine, if you will, something in a blender. So you have a bunch of these in a blender, and they're all kind of spinning and processing and bumping into each other. Now, the second they go into the MRI scanner, they all line up with either the north, let's just say this is the north and this is the south pole of the magnet. Now, you could, quote, ramp the magnet up for, let's say, 100 times, and 51 this will be the north, 49, this will be the south, and vice versa. It doesn't really matter. The poles will switch every time the magnet is ramped up or ramped down. But let's just say this is the north side and this is the south side. Now, remember, we're talking about 1 octillion. So 27 zeros, right? All right, so once they go into the magnetic field, they will all line up with either the north or the south pole. And what I mean is, let's just draw 10 of them just for whatever. So 10, right? So 51% will line up with either pole. So in this case, we'll just say 51% line up with the north pole. So that's 3, 4, 5, and again, only because we're going to use statistics and I don't have to draw out 27 octillion. We'll just make 6 are going the north pole, and for this demonstration, 4 are going with the south pole. So if we do cancellation based on which ones are opposed of each other, that leaves us with just 1. So 4 are going with the south pole, 4 are going with the north pole, and then that leaves us with 1, or let's just say 2. Yeah, 2. Is lined up. And again, you're doing this to all of the protons, all however many are in this imaging volume, 100 trillion. So we hit it with a radio frequency. What is radio frequency, or RF? It is literally the exact same thing as a radio station. So in a 1.5 Tesla magnet, 1.5 T, the hydrogen atom processes at roughly 63.65 megahertz. On a 3 Tesla, it's roughly double this. So I think it's like 128, I think. 63, I think it's like 120, it's like 123 on the 3T trio. 123 megahertz. So it'll be sitting, processing inside of the field at 63 megahertz, spinning at 63 megahertz. Okay, so now we got our proton again, and inside of the magnet there is an RF coil. And so this RF coil delivers radio frequency at, because we're going to be working at 1.5 because that's the most common, 63.65 megahertz. All right. So now we are going to pump RF out of the RF coil into the direction of the proton, and it's going to want to flip 180 degrees like this. If there are other ways it's flipping, I'm not going to go too crazy. This is what's called T1. So it'll flip, and because it started pointing toward the North Pole, it wants to always come back to the North Pole. So we hit it with RF, it flips over. Keep in mind it's always spinning. And it wants to come back to its original resting place. Don't ask me why. So as it's flipped, let's just use 180 degrees. As it's flipped, remember it's going to want to start to come around. It's called T1 relaxation. The second it gets back to its original spot, it it creates an echo. So it's like a blip. So it's a blip. And so as the blip comes out, we are using what's called a receive coil image of, let's just say, now if you were to just flip the protons and listen, all you would get would be in the screen here in the middle, you would just get a white dot. And that's all of the information contained in your echoes smashed on top of each other in one single dot. So if you remember, we always need a three-dimensional object. We have to have three axes, okay? Length, width, and depth. So if we don't get those, we won't get an image. So we also need a phase encoding direction and a RO, or readout encoding. So the two that you're looking at right now in this two-dimensional block, as you see, would be phase encoding and readout. Now there's a third one that's called SS, or slice select. Now the slice thickness, I'm sure you've all seen an X-ray. So this would be, let's just say, one slice. So you're looking at your phase encoding direction here, your readout information here. That gives you your resolution in either, let's just say, X and Y axes, and then the Z axes would be the slice select, and that's how thick this slice is. Now in a typical MRI scan, in this head, they would roughly have an odd number of slices. So 11, 21, 27. The only reason why they do that is if you have 1 to 11 slices, you always have an odd center slice. And that way you can center it up. So how do we get our resolution here and not have a white dot? Well, imagine if this was a grid. We need to change the magnetic field on the person for each group of hydrogen atoms. And I'm going to show you how what's called a gradient amplifier does this. Okay, so I said the whole magnet is at 1.5 Tesla. And imagine person is in the magnet. We're shooting all that RF down into the body to flip everything in the imaging volume. So, remember I said if you didn't have any resolution, everything would just be smacked on top of each other. You'd get a white dot. That's all you would see on the screen. So what we have to do is we have to create slices. So let's just say, for all intents and purposes, we're going to do 1, 2, 3. We're going to do 3 slices, okay? So we're flipping all the protons in this slice, and this slice, okay? So now we need some way to resolve or map it out into 3 X, Y, and Z axes. So we're going to change the magnetic field inside of the imaging volume using a gradient power amplifier. So inside of the imaging volume, on top of the RF coil, is the gradient coil, or GC. Inside of the gradient coil are other coils of wire attached to gradient power amplifiers, and there are 3. They are called X, Y, and Z. So what we're going to do is we're going to use a gradient to change the magnetic field. I'm going to make this easy. Let's just say we're going to start in the center slice, or slice 2. We're going to make our center point, and then we want to change the magnetic field by 30 millitesla per meter. I know this is crazy. Bear with me. So when we turn the amplifier on, we're going to get a positive change and a negative change because we have a positive and a negative terminal on the gradient power amplifier for current to flow through. So if this is the 1.5 Tesla line right here, and we are going to change it 30 millitesla per meter. So this would be, let's just say, the negative side. So this would be 1.49 whatever Tesla. And then this would be the positive side, and this would be 1.51. We'll just keep it simple. So then, using our slice select gradient, we know that this slice is processing at 63.62 megahertz with this change in magnetic field. This one's at 63.63 at this gradient field, and this one's at 63.64 at this gradient field. So now we have a Z coordinate for each hydrogen proton that we're looking for. So that will give us this dimension in our picture that we're trying to look at. So that's the easiest one to explain. The phase encoding direction would be looking down this way, and it would roughly be doing the same thing. And then it's also inducing a gradient on the magnet or the imaging volume, and it's going to step up as it sees, and that's going to give us this dimension. And then there's a readout gradient looking this way, which is going to give us this dimension. The RF and the gradients come on at the same time roughly, and then as it flips, they induce the gradient field, and as it comes back, the magnetization will change and the proton will actually move differently, and then we look for it in a different spot. I know it's crazy, and it's kind of hard for me to explain this without using crazy terminology. But anyway, so that's how they do that. And then if you've ever heard an MRI scanner and it's like, well, that's the current going in and out of the gradient coil so fast that it will actually stimulate the other nerves around it. They'll move. It's called stimulation. It feels like a tingling feeling. Well, anyway, the different noises that you hear are different amplifiers being turned on and turned off for each protocol that you load into the scanner for each imaging parameter. But yeah, so all that's going on in microseconds to get one slice, and then they do it again. So you'll hear it like, it'll go through the slices, and depending on how long the scan time is dependent on what parameter you're looking for. There's weighted imaging, whether it's a T1 weighted image, a proton density weighted image, or a T2 weighted image. I'm not going to go into that because that's crazy. But that's pretty much how it works as easily as I can describe it. This is all what's called pre-processing. This is happening as it's acquiring an image, and as it requires the image, the next thing happens. From our flipped proton. Okay. So the echo then goes to a receive coil, let's say the head coil. Kind of looks like a cage. So the echo gets received by the head coil. It goes through a bunch of wires, and it goes to literally a receiver. The receiver takes what's called the raw data and sends it to a IRS, or image reconstruction system. The imager, as we call it for short, image recon, receives the raw data and turns it into an FFT. An FFT, insert picture, an FFT, or is pretty much a mathematical algorithm that raw data is taken from, and it's used to create a sequence for our raw data into a three-dimensional image. So if you were to look at raw data, it would kind of look like this, roughly. I'm paraphrasing. And then the imager will take the FFT, find our XYZ coordinates, and then turn it into the picture of a knee or an elbow or whatever, or, you know, the person. And then that's it. I hope I didn't bore the heck out of you.